All right, so last time we talked about locally testable codes, and we talked about the left-right Cayley complex. We had this this object. So we had a group G and two sets of generators A and B. And then we looked at this complex where from a vertex G you have neighbors of the form AG, A prime G, so on, and you also had neighbors of the form G times B. So we have multiplication on the right and multiplication on the left, and we saw that this gives us these squares where you go from G to AG and then to AGB and then back to GB, and you get these squares. And so our complex had the vertices that were G, the edges that were whatever they were, and the squares. I'm not going to write them explicitly. Just remind you that the edges, okay, maybe I just remind the notation. Edges that connect G to AG we denoted by this. This is just another name for the edge GAG. Okay. And we also had edges that connect G to GB, and we denoted them this way. This is just the same as the set G and GB. And we had X2 were the squares, and we denoted them AGB. And since a square can have a square can have 4 different roots, kind of where you look from them, then the same square has several notations. You know, there was also A inverse, AGB, B inverse, for example, when you look at this square from this point of view. So anyone kind of have any questions about that? We talked about it last week, but I'm happy to hear any. Okay, so that was the complex, and then we defined the code. We took 2 base codes, CA, which is some linear error correcting code on A bits, and CB, and a linear error correcting code on B bits, and we can assume that A and B have the same size. And then we define the code to be all the functions on the squares so the code is all you put a bit for every square, and then you have some requirements essentially that for every edge F restricted to the squares that contain that edge. This is just some ad hoc notation. Actually, I think a better notation was this. For every G and every A in A and every B in B, we said that I look at all the squares that contain this edge. These are squares that are denoted AG and something. So you range here over all the B's and you get B different squares, and this thing should belong to CB. And similarly, when you range over the A's, so this is all the squares that touch this edge GB, this should belong to CA. That was our definition of code. Just kind of to remind us, so for a fixed edge G, AG, I have many squares touching it. For every B, I have a square that looks like this, right? If there was another B, like B prime, maybe this one, so suppose this is GB prime, then I also have this edge, AGB prime, from AG to AGB prime, and this also closes, because from here to here, by multiplying by A, I get here. So around this edge, I have really an entire book of squares, and the meaning of this restriction is that around this edge, this entire book of squares, when I look at the function on all of these bits, I get a string of B different bits, and this string needs to be in CB. This is what this says. It basically says, for every edge of the A type, look at the book of squares around this edge, and you require the bits there to belong to the code CB. And this requirement says, for every edge of the B type, look at the book around that edge. This corresponds to the set A. You get a string of A bits, and you want it to belong to CA. So that was the definition of the code. And what we saw a few things. We saw that if the codes here themselves, the base codes, have good relative distance, then the entire code has relative distance, assuming that the graph underlying this complex is a good expander. So basically two conditions. One is that the graph here, just vertices and edges, is a good expander, which follows from the fact that, or if you allow yourself to take we take a group G and generators A and B such that the Cayley graph of G with A is a lambda expander, and also the Cayley graph G with B is also a lambda expander. If this is the case, then also the union of these two graphs, which is really the set of edges we have here, itself is also a lambda expander. So once you have that, and if you know that these guys have distance, at least some delta that is bigger than lambda, you immediately get that the distance is delta squared times delta minus lambda. Anyway, it's a positive distance. We saw that. We also saw that you have positive rate as long as the local dimension of these guys is at least 3/4 times the maximum. So the relative rate here is at least 3/4, and you get positive rate. And then most of the effort is to show local testability. Okay, so what's local testability? And we didn't show it completely, and I want to finish. C has positive rate and distance. That's clear. It's also LDPC, low density parity check, because all of the linear constraints that define C are very small, they're very local. They look at a number of bits that's bounded by the degree, so it's very small. And we want to show that C is locally testable. So by what test? So for example, by the test that chooses a random constraint and checks it. Another test that you can think about is choose a random vertex and check all the constraints around the vertex. Maybe that's a bit more comfortable to think about. So for example, sorry about that. So for example, choose random G uniformly from the group with a random vertex and check that a given code word F in all the squares around G is valid. And this is an opportunity to remind us that what do we expect this to look like? So here in the definition of the code, we require that around every edge you belong to either CB or CA, depending which type of edge. And we talked about if I look at an entire code word, but I only look at all the squares touching a specific vertex, what does that code word look like? Right. So, i.e. a tensor code word CA tensor CB And let me remind us that if I had a vertex G, so let me just, if I had a vertex G, and I had some A neighbors, say A1, A2, A3, so this is A1G, this is A2G, and this is A3G, and then there's also the B neighbors, so this is GB1, GB2, and GB3. Then for every choice of A and B here, for example this one, there is a square from G to A2G, to A2GB1, to GB1, to G. So really the number of squares around G is exactly corresponding to A times B. So the squares of G, it's isomorphic to A times B. And so you can really, like, instead of drawing it like that, I can also draw them in a table like this, where I think of this as the first A edge, this is the second A edge, and this is the third A edge, and this is the first B edge. Maybe I'll draw the B edges on this side. The first B edge, the second B edge, and the third B edge. So think of it as a 45-degree rotation. And then, this square is exactly the square that sits on this edge and that edge. And the requirement of being in the code means that my function restricted to this table is every column is in CB. So every column is in CB. These are A edges. So this is like GA1G, this is GA2G, and so on. So on an A edge, the column belongs to CB, and on a B edge, the column belongs to CA. So we can think of the following test. Select a random G, look at this D by D table of squares, and see that what you see there is a correct tensor code word. Okay. And then we tried to analyze this. To prove local testability, you need to prove that, well, if a given F is actually a code word, the test will always succeed, right, by definition. So what you have left to prove is that if the test fails with some probability, this is an upper bound on the distance of F from the code. So you want to relate these two things. One is the probability that the test fails, and one is the distance of F from the code. And you allow yourself some constant here. And this constant is the local testability constant. Okay, and we talked about an algorithm that will help us prove it. So how would you prove such a thing? You start with a given F, and someone tells you that it fails the test only on a small probability. And then the goal would be to prove that this F must be close to the code. So the way we did it was by showing this algorithm. So we had this local correction algorithm. The input is some F. It's not necessarily in the code. And then there was the first step was for each G find some local code word closest to F on these squares. So for every vertex, you look at your function restricted to these squares, and maybe you don't see a code word. If you see a code word, you just take that. If you don't see a code word, you just choose a tensor code word that's closest to what you see. And if there's more than one, just choose arbitrarily. Okay, so that's WG. And now you have a collection of local views per vertex. And how how are you going to get, you want to prove that if the test doesn't fail a lot, then your function is close to the code. So basically you want to generate a new actual code word. So you do this by slowly changing these things until you reach some minimum point. And the idea was to change the local views. If there exists such that changing WG increases agreement, change. And so we're measuring some kind of potential function, which is the amount of agreement between pairs of vertices. So at this point, after we found the local view for every vertex, we can have this picture in mind where, draw it here. So I'm thinking, this is my entire graph. And so I have different vertices. Here is G, here is AG. They're connected, and then, there's many vertices in the graph. And for every vertex, there's this little local view. Every vertex holds its own little matrix, A by B matrix, that is an actual tensor code word. Okay, so everyone has their own little matrix, and they don't necessarily agree. So G got its matrix by looking at the squares around it, but maybe it didn't see a perfect picture, so it took the best guess it could. And maybe, one of the squares between G and AG, it had a 0, but in G's local view, actually this square now has a 1. Whereas AG also looked at its local picture, and actually AG still thinks that this square should have a 0. So now the local picture for AG and the local picture for G don't agree. Okay? Now, if I actually want to zoom in a little bit on this picture, I have two neighbors, G and AG. Now, there's an edge here. So there are squares that sit on this edge. Okay, for every element B, there's a square G, AG, AGB, GB. So for every element in B, there's a square here that touches G and touches AG. In fact, these are the only squares that touch both of them. So this is really like a column here, and the column here, it doesn't have to be in the same, it will be in the same index because it's the same B. So there's a column here and a column here that, sorry, it doesn't have to be in the same index. Here the index of the column, okay, let me draw it a bit bigger. Let me draw it here. I'll draw this again. So I have this matrix, and suppose I have another one. So this is from the point of view of G, and this is from the point of view of AG. Okay, so G has this edge corresponds to GAG. It has this edge corresponding to some other A prime G, and more edges. Okay, and then the way I'm thinking about it, this column, all these squares are squares that sit on the edge GAG. Now for AG, you have the same picture. This one corresponds to AG, AAG. Okay, so this is A squared G. This one corresponds to some other A prime AG, and so on. And one of these guys actually equals G because A inverse is one of the elements in A. So one of these columns is the A inverse. So it corresponds to the edge between AG and G. But maybe here it's the second column and here it's the first column. So I want to use another color. So it could be that this column is actually equal to this column. Okay, this is for neighbors on the A direction. For neighbors in the B direction, I will have a row of intersection. There will be some B edge, it will be a row here, and it will be some other row here. So in my graph here, every vertex has this little A by B matrix, and on every edge there is some row or column of intersection of these matrices. So you can think of this whole construction as a bunch of matrices that are glued to each other in this way. Okay. So going back to the algorithm, every vertex here has this matrix, and you can look at all of the neighbors. So all of the A neighbors correspond to these columns, and all of the B neighbors corresponds to these rows. And you can count how many times you agree with your neighbor and how many times you disagree with your neighbor. And this is the agreement parameter. So basically for every edge we say, does it agree or does it disagree? And that's my global count. And we just locally change our view in case the local count will decrease. So it's some kind of greedy, local greedy algorithm. Okay, and then if a disagreement is 0, then output code word. So we saw that once you reach disagreement 0, it means you have a bunch of local matrices, but they all agree. In that case, you can assign for every square the bit that is written in. Every square has 4 different vertices that think something about it, but if there's no disagreement, they all think the same, and you assign that value to the square, and that will give you a perfect code word. So that's our algorithm. And we saw, so okay, what did we see? We saw that, let's call this code word F tilde. So we saw that the distance between F and F tilde is no more than the number of, the probability of rejection of the test. And the reason was that basically we saw that the algorithm must always halt because there is some integer that keeps decreasing, and the number of disagreement to begin with is upper bounded by this probability of reject, or the fraction of local views that reject. And every time, and in the end, F tilde will only differ from F on squares where something was, at some point this square was participating in a local view that wasn't, that got changed during the algorithm. So you bound all these numbers by the probability of reject. Okay, so is this pretty much clear or? Cool. Okay, so this we saw, and then the second thing, or the important lemma that we didn't prove was that suppose at the end of the algorithm WG is a collection of local views at the end of the algorithm. So suppose at the end of the algorithm the disagreement is not 0. And actually, then the disagreement is large, meaning the number of edges on which you see some disagreement is a linear fraction of all the edges. So E prime, we defined E prime to be the set of edges UV such that WU disagrees with WV. So remember, WU is this matrix and WV is another matrix. They share a whole bunch of squares together. So this symbol means that there exists some square S such that WU of S is not equal to WV of S. So these two local views disagree. we count how many edges have disagreement. The algorithm starts with some amount of disagreement. It keeps trying to reduce it. At some point it gets stuck. It cannot make any more moves to reduce this disagreement. It got stuck, but still it may be that it didn't reach 0. Okay, if it didn't reach 0, then the lemma says it must be that the number of edges was huge, was a linear fraction. And the reason this will prove local testability is because we know that the fraction of disagreement is a lower bound to the probability that the test rejects. We saw that. So it means that if you told me the test almost not, it only rejects with small probability, then I know E prime must be small, and so this event cannot happen, which means that the algorithm will actually reach 0. So there's this gap after the algorithm finished doing these local corrections. The disagreement can either be 0 or very large. And since you know it's not, if you are told it's not large to begin with, it must be 0. Okay, so I want to prove this. This lemma.
May I ask a question?
Yes, please.
When you say it's large to begin with, it might be more than X. Like the guarantees might be smaller than what you would ideally want for a linear code, right? Like the distance, or a code in general. Like if the code has distance d, so you expect to be able to correct d over 2, and this constant might be d over
a million. Absolutely, yes. This is what we're talking now about is local testability. So we're comparing to the fraction of rejecting constraints. There's no guarantee that someone only flipped a bunch of errors. All we know is that we applied a bunch of parity checks, and the fraction that of parity checks that are not happy is small, some delta, and from this we deduce delta over a million disagreement. So yeah.
Would you mind quickly repeating the definition of local testability? Like, does this need to be true for all probabilities or only for like up to a certain?
Oh, okay, thanks. So local testability, if you want to write it in one line, you write it like this. You say you have some test. For example, this is the test, one test that you can think about. The test is for every g, you just look at the constant number of squares around this vertex. So it's d squared squares, and we think of d as a constant. And you say you want to relate the fraction of tests that fail to how far your word is from the code. And we discussed this previously, that you have here two measures that have to do with the string f. This is a string that is not necessarily a code word. One measure is how far it is from this linear subspace. And this measure, maybe it's NP hard to calculate. It's hard to know what's the distance of a point from a space. Whereas this measure is very easy to calculate. You just go over all these tests and you see how many of them fail. So local testability allows you to relate these two measures, which in a general code you don't have this kind of relationship. So that's kind of what's special about LTCs. Now I'm talking here about a slightly different measure, which says either the probability to reject is bigger than some threshold, which has to do with this, or the distance, or I have this property.
T don't need to be constant.
Let me, or star holds. Say again?
And the threshold needs to be constant.
Yeah, it's a constant. So the thing is, if I only prove this star when the probability of rejection is smaller than tau 0, it still gives me the same thing, because I can take the minimum between beta and tau 0 as my new beta. And now I get that the probability, which is, well, if it's smaller than tau 0, then I have star. And if it's bigger than tau 0, then I have here something bigger than tau 0 times greater than tau 0 times something that's at most 1. So it's okay, when you prove local testability, it's always okay to only prove it when the probability of rejection is no more than 1/100 or some threshold. Okay, so that's all good to know. Okay, so now our focus for the rest of this lecture, and I'm going to kind of show this lemma. Maybe I won't do it 3 times, but in some sense we're going to look at this 3 times. Once as a proof of local testability. Then I want to look at it as a proof of some property of a chain complex, like a cosystolic distance of the chain complex. And 3rd time as the distance of a quantum LDPC code. So it's always going to be the same kind of thing. Okay, so let me actually rephrase it a little bit so it will be nicer. So let's say instead WG at the end of the algorithm, I'm going to write let WG. So this is really when I write this, what I mean is for every G in G, I have a little WG, maybe I even write it, which belongs to the tensor code. Okay, so in my mind I have this picture. For every G in G I have a little matrix. Okay, and I want to say that it's minimal with respect to vertex switches, let me call it moves. So what I mean here is that this is a vertex move. We're always thinking about the agreement. We want to make it large or make the disagreement small. And if we can change one of the WGs to improve this, we do it. And we keep doing it until we reach a situation that is minimal with respect to vertex moves and the disagreement. Okay? So it's clear what I mean here? Okay. So then the disagreement is either 0 or, okay, let me just say it's either 0 or it's large. Okay, that's the statement. Okay, so how did we prove such things? We did it for expander codes. When we didn't have all these squares, it was a slightly simpler situation. We had some set of bad things and we wanted to show it's large, and the way we did it is we showed that there is some random walk that moves from one element in E prime to another, and this random walk mixes, so it can't be that you move with high probability. If you start from something in E prime and you move at random and you reach another element in E prime with high probability, this can only happen if E prime is large. This was this Alon-Chang lemma. So this is what our approach will be. We describe a Markov chain. So you can think of it as a Markov chain or a random walk. We'll describe some expander essentially with that's highly mixing. From edge to edge. So the nodes on this graph will actually be the edges, and we'll describe some kind of way to walk from one edge to another, so that the spectral gap of this walk will be very, very small, something like lambda. Okay? And then we will show that if E belongs to the set E prime, then a random step from E lands in E prime with some constant probability. With probability, I don't know, constant, maybe 1/10, something like that. And then remember we had this Alon-Chang lemma that said if you have an expander, so now the nodes in this expander are the edges, doesn't matter, and then you look at the subgraph of all the nodes that belong to some special set, like here it will be E prime, and this is E prime, and then you know that the average degree from a node in E prime to stay inside E prime, the average degree is large, like 1/100. If this graph has lambda expansion when lambda is smaller than this 1/100, this can only be when E prime itself has a constant fraction of the nodes. So this will show that E prime is large. So that's our hope. Okay? Okay, so what will be our Markov chain? We'll have two kinds of move. One move is we remove from E, so starting at E, with probability half, you move to a parallel edge, and with probability half, move to, I'll call it an opposite edge. Okay, so what is a parallel edge and what is an opposite edge? So if I have my edge G connects to AG, a parallel edge is to choose some random B and go to this edge. It connects AGB to GB. Okay? A parallel edge, if your B edge, is to choose a random A and to move to this edge. So basically you choose a square that contains your edge and then you move to the edge that is disjoint. And this random walk, if I continue walking like this from this edge, I take a random B, I move to some other edge, and then I do it again, I move to some other edge. What do you think is the mixing property of this random walk? Like, will I end up reaching all the edges in my graph?
Yes, because just K of G and B is an expander.
That's correct. So it means that if I keep doing that, at least this endpoint, this G, is basically just doing a random walk on the Cayley graph with B, right? So this endpoint of the edge will actually reach every endpoint in the graph. But, do I reach every edge? Yeah?
Oh.
But, like, on every edge you reach, like, the A's that switches between them is the same.
Right, but the level of the edge, I'm stuck with this A. So, I wish I could say, I randomly mix and I'm all happy. I don't. I only mix on a fraction of the graph, only on those edges that have the same label as this one. That's not so bad. It's still, you're mixing on a constant fraction of the graph because the set A is constant size. So let's ignore this. Okay, let's just say that this is a very good expander, moving to a parallel edge. Now, what is an opposite edge? So maybe I leave this picture. This marker is not good. This is a parallel edge. You move from here to here. Parallel. What about an opposite? So this is a bit more weird. Maybe a good name for it would be you move to a weird. But anyway, you start from an edge. You do this weird thing where the edge is, say, UV. First, you choose one of the endpoints, V, and then you move to a neighbor of V, V prime, and then you take an edge, V prime prime and V prime. So this kind of, you move, it came out too parallel. Let me draw it so it's not parallel. So I started from this, and I moved to an opposite edge. Okay, now if I ask you, so the way I moved, let me say it again. I started from an edge. I chose one of the endpoints at random, suppose this one. Then I took a random neighbor of this guy. I moved here. So this is already pretty good, right? Because I'm walking on the skeleton of the graph, so it's a very good expander. And now I take a random edge containing this guy. So this is even better than here, right? Because the label here has nothing to do with the label here, and the end point is mixing. So this is actually a very well mixing walk. Are you kind of convinced by that, or? Okay, so these are the two moves. Now, the claim that I want to make is, one, these are mixing. I'm not going to prove it, just kind of believe it. And the second claim is that if the initial edge was in E prime, then with constant probability, the result, the edge here or here, I should have forgot to highlight this guy, is in E prime.
Can you repeat what is an opposite edge?
Yes, thanks. Actually, maybe I should draw it like this. So opposite edge is this. You start at UV, edge. Then you take an endpoint. So say V. I could have taken V, U instead. Then I take a neighbor, V prime, neighbor of V. And then I take an edge containing V prime. So this is V prime, V prime prime. So if I want to formally show that this is mixing, I write,
A zigzag walk.
it's kind of a zigzag walk, and I can write this whole walk as a series of steps. This is like the down operator, and then I apply the operator of the adjacency of the graph, and then I apply the up operator. So I have here a product of three operators, and the one in the middle is very well mixing, so the entire thing has very small second largest eigenvalue. Okay, so and the claim, if E is in E prime, then the random walk reaches, E prime, again in E prime, with probability that's some constant. The meaning of the word constant here means that it's some absolute constant that doesn't depend on the spectral norm of the graph. So lambda can be much smaller, and then we can just by this use the Lorentz-Chang lemma and get that E prime is large. Okay, and how do we prove this claim? Okay, so now we need to, okay, so this was all games about these walks, and we need to remember what the code looks like. So suppose we start with an edge in E prime. So what does that mean? Say it's an edge between G and AG, and G has its own little local view, this matrix, and AG also has its own little local view. So what does it mean that this edge is in E prime? It means that these local views disagree. Now they share a whole column of squares, and since this is a code word and this is a code word, the fact that they disagree in this column means that, it's a code word in the tensor code, so the string just in this column is a code word in CB. Right, so basically they disagree on a code word in CB. So what does that mean? Can they disagree on only one square, for example? No, they must disagree on a fraction of squares that corresponds to the distance of CB, because these are two different code words in CB. They disagree exactly on, that's the meaning of distance. So they disagree on some delta fraction. Okay, so the conclusion is when you have an edge of disagreement, a delta fraction of the squares around this edge get different values from the different local views. So now think of one of these squares. Okay, so maybe just draw it here. So I have here G and AG, and I have this square. Now the local view of G thinks that this square should get a 0, and the local view of AG thinks that this square should get a 1. Okay? Now there's two other neighbors here. I don't even need to know what their names are. But this neighbor must think either 0 or 1, right? So either agrees with this guy or with that guy. It can't be that this neighbor agrees with AG, this neighbor agrees with this neighbor, and this neighbor also agrees with this. In other words, if these disagree, there must be some other edge of disagreement, right? So I started with one edge of disagreement, and now I deduce that either this or this or this edges must disagree. So that's very good, right? It looks like the kind of thing we're looking for. We want to show that if you start with an edge in E prime, you landed in another edge in E prime with a good probability, and here the probability is, what is it actually? If I move from this edge to one of these three edges, what's the probability that I land in a disagreement? So what would be the walk that corresponds to what we did? We started from an edge. We took one of the squares on this edge, and then we took one of the three edges in that square. Okay, so with probability at least the distance of CB, which is some delta, we landed in a problematic square. And then with probability 1/3, the edge that we chose is going to be in E prime. So with probability delta over 3, one of the edge that I landed in, either this one or this one or this one, is in E prime. Okay, so actually, why am I bothering to do this complicated random walk? Now we found a better, simpler random walk that has constant staying probability, delta over 3. It's at least delta over 3, which is great. I mean, the bigger the better. And we think of delta as a constant, so lambda is going to be much smaller than delta. You think of delta as like 1/4. So I have here a good random walk that has good staying probability. Why am I not using this random walk? Thanks. Yeah, it's not mixing enough. So somehow this random walk has two different kinds of edges. If you move from this edge to this edge, for example, that sits on this vertex, then you see that you remember this vertex AG. Okay, and you do it again, maybe you still remember AG. And so the set of all edges that touch this vertex is a set of edges that, with respect to this random walk, you kind of get stuck in this set. You don't leave it fast enough. You get stuck in it with constant probability, 1/3. So this means that the mixing of this random walk cannot be better than 1/3. Do you see this roughly? Okay. I'm now making up some random walks, and I'm trying to ask myself, is this random walk mixing or not? Okay, so I'm making up some random walk. For example, I move from edge to a square and then to one of the edges in that square. And I hope that it's a very well mixing walk, but actually it's not. And what is a counterexample? A counterexample would be to find a set of edges and to show that the random walk doesn't leave this set with high probability. A walk that's really excellent mixing random walk is a walk that if you have a small set of nodes on which you're walking, then in one step you leave with high probability. With high probability. It's not enough to leave with some probability half. You need to really leave quickly. And the set of edges that all the neighbors of a specific vertex, so one of these edges, for example this one, now choose a random square on this edge. Doesn't have to be this one, it can be another one. And then choose one of the edges on that square. You could, with probability 1/3, still pick an edge that contains this vertex. So this walk has only probability 1/3 2/3 leaving probability of this set. So it's not good enough. Okay, if you didn't follow me exactly, just let's take as the gist of the matter, the random walk that moves from this edge to one of these three is good in that, indeed, one of these three will be in E prime, but it's not mixing enough. It gets stuck in the set of edges around the vertex. So we need to do something more clever. Right, so what is the thing that's more clever? Okay, so let me say that and then we can take a break. So we're going to separate the edges of the square into two types. The first type is the parallel edges. From this edge, I look at a random square, and then I move to the parallel edge. This random walk, we already said it's mixing. So if a good fraction of these edges is in E prime, I'm going to be happy. So suppose they're not. Suppose all of the parallel edges are actually not in E prime, or not all, but suppose only a tiny fraction is in E prime. This means that many of the edges adjacent either to AG or to G must be in E prime, right? Because you need to choose either this one or this one. Okay? So what does this mean? It means that this vertex has many edges adjacent to it that are edges of disagreement. Okay? So, to say it one more time, if the walk that goes from this edge to a parallel edge doesn't stay in E prime with good probability, meaning many of the parallel edges are not in E prime, I'm going to say that in this case, I'm going to say some stuff, and in the end, it will lead to saying many of the opposite edges will be in E prime. Okay, so what we're saying is that either many of the parallel edges are in E prime, or many of the opposite edges are in E prime. And my random walk will go with probability half to either of them, so I will land in E prime with constant probability. Okay, so why? Suppose we tell me that not many of the parallel edges are in E prime. This means that many of the adjacent edges, either on this side or on that side, or both, are in E prime. Why does this mean that there's many opposite edges that are in E prime? Okay, so let me just say this. So claim if so fix E. If almost none of parallel edges are in E prime, then so E is some, I don't know, UV. Many edges adjacent to U or V are in E prime. Okay, this should be clear, right? When I say many, I mean a constant fraction. Why? Because how many neighbors does a vertex have? Basically 2D. If suppose that we assume that the cardinality of A and the cardinality of B is the same. Then this guy has 2D neighbors, and we're now looking at just D of them, and out of the D of them, some constant fraction are going to be in E prime. So it's still a constant fraction of 2D. Okay, so now I want to say if, okay, so this is one point. The second point is that if V has many adjacent edges in E prime, let me call V heavy. It sees many edges of disagreement. Okay, so if V is heavy, I want to say that many edges that are opposite V are in E prime, and by opposite V I just mean now I'm already here, so I just move to a neighbor and then take an edge. Okay. Okay, so now let me say why is that, and then we can take a break. Yeah. Okay, so this is the situation. I have a vertex. Okay, maybe I try to use this picture. I have a vertex, let me call it G, okay? And many of the, and it has this local view, it has its little matrix that is the local view of G. And you know that it disagrees with many of its neighbors. And now I want to say, I'm interested in edges of the following form. I'm interested in edges that close a square in G. Okay, these kinds of edges, okay? So for every square that contains G, 2 of the edges of the square are adjacent and 2 of the edges are closing edges. I want to say that many of these must be also edges of disagreement. Okay, and you get to these by moving from G to a neighbor and then taking a random edge containing this neighbor. If you want to be completely formal, you need to switch colors. Like if you move to a B neighbor, then you need to move to an A neighbor. But this is only affecting my probability by some constant 1/2, so I don't care. Now, why are these closing edges going to be edges of disagreement? Suppose they weren't. Suppose G doesn't agree with many of its neighbors, but all these neighbors, they agree with each other, meaning all of the endpoints here that close the squares agree both with this guy and with this guy. Suppose they actually agree all the time, 0 disagreements. So what am I saying? Look at all the vertices that are 2 away from G. These are the vertices of the form AGB, right? Like this guy is A1GB3. All the vertices of the form AGB. And suppose they agree with all of the neighbors of G, this way and that way, perfectly. What does it mean? It means that what I want to claim is that it means that all of the neighbors of G are in perfect harmony, and only G is kind of ruining the party. Okay, so G should just change its value. So what I really want to show is that if your neighbors are in perfect harmony, there must be a better value for G. But by our assumption, G is locally minimal. I don't know where I have it written, over there. We said that we finished the algorithm and we made all these improvement moves. So this can't be. Okay? So why am I saying that if the neighbors are in perfect harmony, there must be a better move for G? Let's try to understand that. Okay, so in my mind, G is some matrix, and each of the A neighbors of G has an opinion about one of the columns of this matrix. Each of the B neighbors of G has an opinion about one of the rows of this matrix. So G can collect the opinions from all of the A neighbors, and it will get a matrix whose columns are in the code, but maybe the rows are a mess. It can also collect the opinions from the B neighbors, and it will get a matrix where the rows are in the code, but the columns might be a mess. And what does it mean that these neighbors are in perfect harmony? It means that these two matrices actually agree perfectly. So you have a rows matrix and a columns matrix, and they're actually the same matrix. So it means that this matrix is in the code both for all the rows and for all the columns. So G should actually move to be that matrix. It will then agree with everything perfectly. Okay, so what I said now is when everyone agrees perfectly, and I need to have a statement that is approximate. So this is what we call agreement testability, and I'll define it after the break. It's a property of the code CA tensor CB. So not every tensor code has this property, but it basically says if you have two matrices, one is a rows matrix and one is a column matrix, and you see that they agree almost always, if the weight of this is small. Why did I write plus? When I add two matrices, I get a 0 when they agree and a 1 when they disagree. So the weight is exactly how often they disagree. If this is small, then there exists some tensor matrix. It's a new one. And when I draw this, I mean that it's in the code both in the columns and in the rows, close to both of them, to each of them. It's a definition. It's a definition of when this code is agreement testable. If whenever the rows and the columns agree, there must be a tensor reason for it. This is a definition, and if we have this definition here, it means that the neighbors cannot be in harmony because otherwise G would have changed to this tensor guy. And since we're already at a locally minimal collection, it means that the neighbors must be in a lot of disagreement, and so there are many opposite edges of disagreement. Okay, so let's take a break, and then we will talk about agreement testability, and I will show actually that this is exactly equivalent. I think this is really cool. This is exactly equivalent to coboundary expansion of what? Of a specific chain that has to do with the tensor code. So I need to define a chain complex here, and I'll show that the coboundary expansion of this chain complex is exactly the agreement testability here. And then, suppose we do that, we will get that we start with a Cayley complex, and we make these blue assumptions that the graph are expanders, and the codes have distance and rate. And if we also assume, that CA tensor CB is coboundary expander or agreement testable, whatever term you want to use, if you also have this, then you get that the entire thing is a locally testable code. Okay, so finally we can take a break. Okay. Okay, so where were we? We are in the situation that we know that our vertex, we said it's heavy. So we started with an edge, we said either many of the parallel edges are in E prime, great, otherwise one of its endpoints is heavy. Suppose we focus on that one. So what does it mean for this vertex to be heavy? It means that it disagrees with many of its neighbors. So now let's see kind of what's going on. So this guy has its own opinion, it's a tensor code word, but it can also kind of go around its neighbors and ask for their opinion. So every A neighbor of G has an opinion about an entire column. So I can go to each one of my neighbors and ask, what do you think of the first column? What do you think about the second column? And so on. I collect all of these opinions, and I create a matrix of opinions from my A neighbors. Similarly, I can go to my B neighbors, and each one of them has an opinion about a row. And so I can create a matrix of opinions from the B neighbors. Now these matrices are like, I copied what my neighbor thinks. It's not what G thinks. Okay? And now, G itself disagrees with many of its neighbors. And we're arguing that it can't be that the neighbors agree with each other. What does it mean that they agree with each other? It exactly means that, this neighbor thinks about some, I don't know if it was a column. This neighbor has a row, and the intersection of this row and column is exactly this square. So every pair of neighbors can ask themselves if they agree on the bit of intersection. You exactly see it. It's like this column and this row, and there is some bit of intersection. And this measures what's the probability of choosing a random B and a random A and having them agree on this square. And if this probability is large, suppose it's large, then I'm happy, because then I know that this guy and this guy disagree on this square. So this guy in the middle, it must either disagree with A or disagree with B, because these disagree. So this edge must be an edge of disagreement, or this edge must be an edge of disagreement. So the point is, if my neighbors, if the weight of the matrix that's the sum of these two is large, I have many edges here, these closing edges that must be in E prime. And so this random walk of going to an opposite edge will hit these edges with constant probability, without going into the calculation. So the property that I need is exactly what's written here. It's the following property. If you have two matrices, one of them consists of row code words, and one of them consists of column code words, and if they are close to each other, so the weight of the sum is small, it means that the distance of this to this is small, then there must be a tensor code word that's close to both of them. Now we saw this in a previous lecture, and I showed you even an example where this is not the case. I showed you an example of a tensor code where this is a low degree polynomials of degree q over 2, over a field of size q, and these are low degree polynomials of degree q over 2. And we saw that you can take these matrices, we actually had an explicit definition, such that the sum is very small, it's the identity matrix, so it only has ones on the diagonal, and zeros everywhere else, so the fraction of ones was tiny. Nevertheless, there was no close by tensor code word, so this is certainly not always true, but in some cases you do have it, and if you take these codes, then the argument goes through. So now I want to describe this property in more cohomological terms. Okay. Okay, so I'm going to define, I'm talking now about tensor codes. And let me, to be easier for me to just think of one code, a subset of n bits, and the dimension is k. Okay? And I'm starting with k squared bits. So, so the tensor code C tensor C consists of n by n matrices where every column is in C and every row is in C. This is what this tensor, this is a subset of 0, 1 to the n squared. Okay, so now I'm looking at this chain where from k by k matrices, these are the messages. First, I encode to k by n, so I basically make it like a wide matrix. I also encode it to n by k, so I make it into a long matrix. So this is, and how do I do that? I basically, let me see if I get it correctly. So let's hope that this is fine. No, it's actually wrong. Yes. So think of G as the generating matrix of the code. So it takes k bits and it outputs n bits. Then basically this operator applies G on every row of this string separately. So from this, you apply this operator, you get this, by just encoding each message to an entire row. So you stretch it horizontally. And this operator is the same that goes on the column, so it stretches each column vertically. Okay? So this is a linear map from k squared bits to k by n bits. And now we move to z2 to the n squared, where I now apply, for every column here, I stretch it using G again. So now I apply G tensor I, and here I do I tensor G. And here I stretch every row to an entire row. Here I stretch every column to an entire column. So this map takes this matrix and makes it into an n by n. This map takes this matrix and makes it into an n by n, and I'm summing them. So every bit here is the sum of this and that. Okay, so I defined the linear map by hand waving, but do you kind of understand the linear map? Okay.
Can I go back and ask a question about the agreement testability?
Oh, sure, yes.
So what is the weight of WT?
Okay. So you have the n squared, the object has n squared bits, so d squared. The weight is just the normalized, so it's a number between 0 and 1, the fraction of non-zero bits.
Okay.
So you're saying basically that if less than a small, if a small fraction of those bits is small, what am I saying? If the weight is small, you must be close to a tensor code word.
And what do you mean by the horizontal versus? guess I missed the original explanation.
Okay, let's say it again, and then I'm going to say it again in that terminology, but it's good to also first have it here. So agreement to stability is the following. Given, let me write some words. Given M row, which belongs to CA tensor identity, and M column, which belongs to identity tensor CB. So what does this mean? I mean here that every row belongs to CA in M row, and here every column belongs to CB in M col. Okay? If the weight of M row plus M col is small, so you're given two matrices. You sum them up and you see how many bits are left. If this is small, then there is a new matrix M, which belongs to CA tensor CB, such that the distance, okay, it's great that you asked this because it's good to have this definition written formally. Let me make some room. Okay, if the weight, okay, let me write this. If the weight of M row plus M col is small, then there exists some tensor code word such that the distance of M to M row plus the distance of M to M col is some beta times epsilon. Maybe I write it like this: beta times the distance is small.
And is M allowed to be the zero code?
And you know what? Actually, let me be absolutely precise here. M is allowed to be the zero vector. The zero matrix is a matrix in the tensor code. That's fine. But actually, let me be even exactly precise. So I'm not going to measure the distance. I'm going to measure the probability over a random row R, that M row, at the row R equals M at the row R, plus the same probability, but now with a random column, M col on a random column equals M on a random column, then this is smaller than epsilon. Okay, so I'm sorry for, it looks a bit messy, but let me read it and then maybe it will be clear. See. So I have here two matrices and I'm computing the weight of these things, and this is the weight is some number between 0 and n squared, and I normalize them so I get a fraction that's between 0 and 1. The fraction of indices where they disagree. And I denote this fraction by epsilon. Okay? Now I'm saying that beta agreement to stability means that there must be some tensor matrix. It could be the zero matrix. Any tensor matrix is legal, such that if I measure on how many rows does it disagree, with M row, and I also measure on how many columns does it disagree with M col, and I should actually take the average of these two things, then this number is small. When I multiply it by beta, it will be smaller than the same epsilon. Okay, so this is my definition. Does it answer your question?
Yeah.
Okay, so now I have this definition on the board. Go back to this weird chain of linear maps. So the linear maps are, you take a k by k object. This is k by k. First you stretch it horizontally and then vertically. Now it's n by n. You basically encode every row and then you encode every column. Or you first encode every column and then encode every row. Okay? And here you add the two things up. Okay? So if you did that and you started with something here, one can check, it's easy actually, that if you first do the rows and then the columns, you'll get the same result as if you first do the columns and then the rows. So you start from here, you apply this map, and then this map, you get 0. Okay, so we're going to look at this as if it's Z2. K squared goes to Z2 times 2, okay, times Kn cross Z2 to Nk maps to Z2 N squared. Okay, so I'll call this delta 0 and call this delta 1. So I have here a chain of linear maps, okay? From here to this pair of spaces, so it's just a product, so I'm writing it in on one line. And then from here, delta 1 maps me here. How does it go? First, there's this part of delta, and then there's that part of delta, and I sum them up, and I get to an n squared matrix. And what we just kind of convinced ourselves is that if you first apply delta 0 and then delta 1, you get 0. So it's a chain complex. So this is a chain complex. Okay, this is a chain complex.
Why it is 0?
Delta, okay, delta 1, delta 0 is 0. If you start from an element here, and you first encode it by rows and then by columns, you'll get the same thing as if you first encode by columns and then by rows. And since delta 1 adds these two things up, it will add something to itself, it will get 0. Okay. Okay, so it's a chain complex, that's good. It's also exact. Also exact, meaning exact, I don't know if we used this term before, meaning that the kernel of delta 1 equals the image of delta 0. Okay, so if I'm here, I can ask myself who are the cocycles. It's the kernel of this map. It's the guys that go to 0. And I can also ask myself who are the guys that come from below, the image of delta 0. We know that the image of delta 0 is contained in the kernel of delta 1. This is what this means. And exact means that these are the only guys. There's nothing else. And the reason for this is that, okay, so what is the reason for this? What is the image of delta 0? I take k squared bits, and I now have one kind of short and wide matrix and one narrow and tall matrix. This is the output from here. Now, how can I think about this matrix? I can think about it. Every k-bit string tells me a specific code word in C, because I will encode it. Without adding any more information, I will get here a row I will get here a code word. So really I can think of this object, an arbitrary object, not something that came from below, just an arbitrary object, as I can think of it as a row matrix. It's just, you can describe it by n times k bits, but you can think of it as a matrix whose rows are in C. Similarly, this guy, you can think of it as a matrix whose columns are in C. And indeed, once you apply this map, you're actually moving from this representation to the representation of a matrix whose rows are in C, and here a matrix whose columns are in C. So let me kind of draw it. So when you move here, just before you do the addition, what you get is a matrix whose rows are in C. And when you move here, just before you do the addition, you get to a matrix whose rows are in C. Okay, so you move from here, just before you add them up, you get to this and to that. Okay, and now what is the kernel of delta 1? It's exactly all those pairs of row and column matrix whose sum is 0. What does it mean that the sum is 0? That this is equal to that. What does it mean that they're equal? That you have a matrix whose rows are in C and columns are in C. It's in the tensor code. So how many matrices? So this is the kernel. Any pair of strings here that's in the kernel must correspond to a tensor code word. But these are exactly all the tensor code words. So that's why the image of delta 0 equals the kernel of delta 1. So kernel delta 1 corresponds to a tensor code word, and the dimension of these is exactly k squared. So it must equal to the entire image of delta 0. Is this kind of clear? Nice. So you already see that these two row and column matrices appear here, right? Okay, so what does it mean? So I want to say that let's try to understand what is the coboundary expansion of this thing. Okay? Let's see if I can fit it in this part of the board. Okay. So what is coboundary expansion of a chain complex? Remember that it's saying if I have some one chain in the middle, so for some function in Z2, let me just write 2nk. So it's n times k plus k times n. So basically what is this F? F is a pair of a row matrix and a column matrix. Right, so I have something like that. What I want to show, I want to compare the weight of delta 1F compared to, this is going to be the coboundary expansion, some constant, times the distance of F to what? Well, either to the kernel of delta 1 or to the image of delta 0, they're all both the same, right? So to the image of delta 0. Okay, what is the image of delta 0? The image of delta 0 is you start with something that has k squared bits, and then you stretch it once this way and once that way, and you get to something that at least has the same form as F. Okay, but every element here really corresponds to one tensor code word, because the row matrix and the column matrix that you will get are the same. So this exactly corresponds to, I want to say that this exactly corresponds to what's going on here. So I'm saying that F is equivalent to a pair of M row, M col, right? Because F is like something like this, and I can stretch it to get M row and M col. This is a one-to-one correspondence. Okay, what is the weight of delta 1F? Delta 1F is the following thing. You first stretch it, and then you add these two things. So it's really the weight of M col plus M row. So what I have here is really the weight of M col plus M row, exactly. And now I want to figure out what's going on here. So here, I'm asking myself, what's the distance of F to this thing? Now, how do I measure distance? I didn't specify it. I made a pedagogical mistake. I should have said, what should I have said? I think I should have had it like this, zk to the n, zk to the n, so that it's like there's 2n elements here, each one has size k, so that when I measure the distance between two things like this guy and this guy, I'm going to just measure on how many rows do they differ. And when I measure this guy compared to some other one, I'm going to measure on how many columns they differ. This is how I need to define it. And then it will exactly correspond to the probability or the fraction of rows on which, so this will exactly correspond to this definition. I don't want to spend more time because I don't think I will be able to say it better than if you just think about it. So in other words, I mean, this definition is like very old, and this is a much more new way to phrase it, but it just kind of completely coincides with coboundary expansion of this weird diamond chain. Okay. And I want to say that it's not only that tensor codes can be described in this weird diamond chain, actually the entire left-right complex can be described as a chain complex. So let me try to do it. Okay. Before I do that, maybe do you want to ask any questions? Okay, so this is coboundary So now I want to say we have this code, but really we also have this the following map. So we have x0, x1, and x2. In x1 we actually have two kinds. We have xa1, these are the A edges, and we have xb1, these are the B edges. And let me put, for every edge, let's put k bits. And for every vertex, let me put k squared bits. So let me do it nicely. So z2 to the k to xa1 and z2 to the k to xb1. And for every square, I'm just going to put a bit. And so you think of these two spaces as just the direct product of these two spaces. There is a cross here. Okay, now there's a linear map that goes like this, and another one that goes like this. So if I want to write it in condensed form, I'll have z2 to the k squared to the x0 moves to z2 to the k to the x1. I'll say what the map is, z2 to the x2. So I'm saying that the kind of the code that we already defined can be placed on such a picture. And I'm not going to write formally the definition of the map. Instead, I want to describe them as a story. Okay, so starting out, we have an element here. What is an element here? It's a collection of WGs, or it's a collection that for every vertex, x0 are all the vertices, for every vertex, you have k squared bits, an element of k squared bits. Now if you want, every element of k squared bits can be viewed, you can encode it by the generating matrix of CA and CB, and you will get a code word of CA-CB. Okay, so you can think of this as a collection of code words, one per vertex. This is exactly what we had over there, right? This is an object that we looked at. Here we had, for every vertex, we had this little matrix. So it's a natural thing. For every vertex, we have a little code word. Now, the vertex can, now we want to encode, we want to move from the values on the vertices to the edges. So each vertex will look around at its edges and distribute the code words. So a vertex looks at all of its A edges, and for every A edge it will put a row, one of the code words. Right? So if a vertex, let's think of it here. Suppose a vertex has all these B edges and all these A edges. I'm thinking this is the vertex G, and these are all the A edges. The vertex has this whole matrix of values. So on every A edge, this vertex is going to send this code word. So the vertex sends to the A edge touching it an entire code word. To another A edge, another code word. And to a B edge, it also sends a code word according to these rows. Now an edge has two endpoints. So the edge receives a column from one endpoint and also a column from another endpoint. So the edge sums these two things up. So this is the story of how the linear map goes. Okay, every vertex has a matrix, and now the two matrices contribute to the edge. So we already saw this here. For example, here are the two matrices, and maybe they disagree, maybe they agree. On the edge, I'm going to write the sum of this column plus this column. Okay, if they agree, what I have here is 0. If they disagree, I have some code word here. Okay, so we started out with a collection of code words on the vertices, tensor code words on the vertices, and after doing this map, what I have is on every edge a code word. If it's 0, it means that these two guys agree, and if it's non-zero, it means they disagreed. Okay, so it should be clear, this part. Okay, now suppose I have an element here, so it doesn't necessarily have to come from below. Now I'm thinking, I have my graph. On every edge, I have a code word. I don't know where it came from. Now what do? This edge, so I have an edge, it has an entire book of squares on it, right? So the edge just distributes its bits to the squares. There's exactly the correct number of bits. The code word has length b and there's b squared, so the edge just gives a bit to each square. Okay, now the square receives bits from it has 4 edges, so it receives bits from all 4 edges. Okay, so the square adds these things up. That's it. That's how you define this entire map. Okay, let me erase this because it's the same. It should be kind of clear that this is one space, this is one space, there's a delta 0 here, and there's a delta 1 here. Okay. We define this map, and what I want to say is that you already saw that what we proved over there, we have a collection of WGs and something happens there, it can be phrased in these terms. Okay, let's see if I wanted to say something else first. Okay. First I should say that this is itself a 2-chain, meaning that delta delta is 0. So 2 things I want to say. First, claim delta 0 and then delta 1 equals to 0. So if you started from a collection of local views per vertex, and you sent them to the edges, so now every edge kind of contains really the difference between the row in this matrix and that matrix. And now every square gets the bit from 4 different vertices. I'm claiming that this will every square see a 0. Any idea why that's true? So I start with something on the vertices. Delta 0 moves me to something on the edges, and delta 1 moves me to something on the squares, a bit per square. So now, if I look at a square, for example, this vertex, it had an entire matrix, and then it sent some row to this edge, and some column to this edge. And then from that column, the bit corresponding to this square came, and the bit corresponding to this square came again, and it's the same bit because it came from the same tensor code word. So the bit corresponding to this square so this vertex had a tensor code word, and one of the bits in this tensor code word corresponding to this square, and this bit got sent to this square both through this edge and through that edge, so it canceled each other. And the same here. The tensor code word here, there was some square that corresponded to this square, and it got sent twice. Well, anyway, maybe it's hard to follow this way, but things get sent twice, so you get 0. The second claim is that I want to understand is suppose I have some 1 chain, so I have some f that belongs to this middle guy, so z2 to the k to x1. And actually assume that f is what do I want to assume about it? Okay. It will be more convenient for me to think of this like we did before, that on here it says that on every edge you have k bits. But let's let f prime be the same, but instead I'm thinking of it as belonging to the code raised to x1. So how do I move from k bits to d bits? I just encode. Okay, so on A edges I use the A code, and on B edges I use the B code. Let's pretend it's the same code, C0, okay? So if I have a k-bit string on every edge, I can just stretch it to an n-bit string. So it's okay? Okay. 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 If f is locally minimal with respect to vertex moves, so this is not defined, I want to define what it means. This should be similar to what's going on here, okay? If it's locally minimal with respect to vertex moves, then the weight of f, actually I don't need the f prime here. The weight of f is omega of 1. Sorry, f, okay, start like this. I'm starting with a non-zero f, okay? And I'm saying if you cannot make it even smaller by adding things from vertices, so I have something here, I can always take an element here, like for one vertex I have some matrix here, I encode it and I add it. I can always do that. And after I've finished doing it and reduced the weight as much as I can, my function is called locally minimal with respect to vertex moves. Okay, so if I have an f, I have some chain here, and I'm going to try to understand what is the smallest weight of a chain here. Okay, so some chains actually come from below, so they're the image of delta 0. These chains, for me, I think of them as having weight 0. Because really what I'm looking at is chains here that want to be in the cohomology. So they want to be in the kernel, but not in the image. Okay, so I'm saying if my chain is not cannot be zeroed by adding guys here, then I'm going to add as many as I can. I reach some point, and I'm going to now claim that the weight is at least a constant fraction. So this is corresponding to saying that all members of the cohomology have high weight. Okay, so this is supposed to be equivalent to what we had here. But maybe let's take a break and I can say it more clearly. Okay, so I want to leave this for a minute because I want to say a little bit about the quantum LDPCs on this square complex. So it turns out that once you have this kind of two-chain, if you have some more properties of the code CA-CB, then you can actually get from it a quantum LDPC code. So let me say a little bit about these objects. I'm really not an expert, but I will try. Okay, so quantum error correcting codes. Okay, so just like in classical coding theory, also in quantum information, errors can happen, and actually this is a big deal for quantum computing because errors happen all the time. And if you ever want to have a quantum computer, you must be able to be resilient to some amount of bit flips. And so the way there's a certain kind of error correcting codes that are called stabilizer codes, and even a subclass of that are called CSS codes for the three people that invented them, Calderman, Shor, and Steen. And these codes, you think of you have a system of n qubits, so these are the n qubits. And a qubit, so n qubits, there's this space of dimension 2 to the n in which a specific quantum state on these qubits exists, and the code is just a subset of these quantum states. And the way this subset is defined is by parity checks. However, qubits can be measured in more than one basis, so if you even want to measure if this bit is 0 or 1, there's an infinite number of bases you can use to measure. And so we focus on two different bases. One is the x basis, and one is the z basis, and by linearity, any other basis is a combination of them. So it's enough to focus on, you measure every bit either by an x or by a z basis. And so the code is defined by either parity check on x's or by parity check on z's. So one way to draw it is you draw a parity check matrix like this, where these are the bits and these are the x checks. So by this I mean, you should think of it, there's a parity check that XORs these 3 bits, but it's not really XOR.
What are x and z?
X and z are two bases. One is the 0, 1, and one is plus minus. 2 bases for a quantum qubit. Okay, and so a quantum code is given by 2 parity check matrices, and this is just normal parity check matrix. One is HX, it's talking about n bits, and one is HZ, and it's talking about n bits. So the bits are here in the middle, and I have the z checks, it's the same. So this is a z checks. Okay, so I don't know, like this. But a quantum code is not defined by just any pair of classical parity check matrices. There's an additional constraint, and the constraint is that the rows of HX must be perpendicular modulo 2 to the rows of HZ. And the meaning of it, so what is a row here? A row is just a parity check, okay? So it means that every check here, if you look at every other check, the intersection of these 2 checks must be on an even number of bits. Okay, so for example, these intersect on an odd number of bits. So this check touches these 2 bits, and this check touches these 2 bits, so it's even. So that's okay. Anyway, if you just look at this part of the if this bipartite graph, this is the adjacency matrix, this bipartite graph, this is the adjacency matrix, and you want that every pair of guys here intersect on an even number of bits. Now why do you want that? Because really, what are these parity checks? Really, what's going on, if you have here, say, 1, 1, 1, and the rest are zeros, the interpretation of this is that you have an operator that, this is like you measure in the x basis, or not measure, this will flip an error in the x basis. On the first 3 bits, you flip them, and on the rest, you put identity. So this is just an operator that you can take it and operate on your quantum state. And the way error correcting code is defined is to say all of these operators that correspond to the rows in HX, you want the quantum state to be invariant. So when I take my quantum state and I apply this operator, I stay inside the, I'm still in the same state. Okay, so what this means is that the code consists of all vectors that are eigenvectors of this operator. There are also eigenvectors of the operator corresponding to the second row and the third row. So the code is the set of vectors that are eigenvectors of all of these and all of those, but these guys are with the z's. So it's like, an example would be something like this. So you have a bunch of operators defined by these matrices, and the code is just all the vectors that simultaneously are eigenvectors here and here with the same eigenvalue of 1. That's how a code is defined. And okay. And now, how can you be an eigenvector of 2 different operators? The operators need to commute. Now, these operators, no matter where you put x's and where you put i's, they will all commute with each other. These operators will also all commute with each other, so you need these guys to commute with those guys. Now, x and z themselves don't commute, but they anti-commute. xz turns out it's equal to minus zx. Okay? So, if you have an even number of xz's, the minuses get cancelled and it looks the same. So it turns out that this is exactly the property that's enough, which is that every operator here intersects, the number of z's here intersect the number of x's here in an even number, which means exactly that the rows of hz are orthogonal to the rows of hx. Now I'm really, as you see, I'm really not an expert on this. I think Thomas Vidic will give a whole course next semester on this topic. So for me, let's just say that a quantum CSS code is given by two parity check matrices HX and HZ, such that the rows are orthogonal. And we have the following thing, the dimension of the code is equal to the number of qubits minus the number of constraints. So how many constraints do I have? The number of rows here and linearly independent, and the number of linearly independent rows here. So minus, Rx minus Rz. That's the dimension of the code. And the distance of the code, okay. So before I say about the distance, I'll say that every code word corresponds to the kernel of HZ divided by the transpose of HX. I think. Let me make sure I'm not making a mistake. Okay, let's write it differently. Kernel of HZ is really CZ, right? So it's the code of Z divided by the code of X perp. So every code word of CZ is potentially a code word in our code, but the fact that these guys are perpendicular means that CX perp, what is CX perp? This is all the code words. This is now a classical space. It's just a subspace of 0, 1 to the n. This is all the code words in 0, 1 to the n, such that W is perpendicular to F for every F in CX. Okay, so this is just the dual code. It's the set of strings that are perpendicular. This is all in mod 2 inner product to every word in CX. Okay, and the fact that HX, the parity checks of X, are exactly the guys that span CPerp. This is the span of HX. Okay, why is that? Because CX equals the kernel of HX, which equals the set of W's such that HX W is 0. Right, so it means that these are exactly the W's that are inner product 0 with every one of the rows in HX. Okay, so it's exactly the perp. Okay, so
here you treated it in the classical way?
This is all classical.
The CZ as well?
Yes, the CZ as well. I just don't write it twice. It's the same. These are classical. This is classical. Okay, so there is some quantum interpretation that I said a few words about, but now I forget it. And now what I have are two classical matrices, and the rows are perpendicular, meaning every row here has mod 2 inner product with every row here, 0. Okay? And now I can look at CZ are all the words in the kernel of HZ, and I claim that every row of HX is in fact in the kernel of HZ, right? Because being in the kernel of HZ means you need to be perpendicular to every row here, and HX indeed is perpendicular to every row here. So HX, every row in HX is in CZ, and also every span of every row in HX is in CZ. So first we notice that CX perp is contained in CZ, and similarly CZ perp is contained in CX. Now it's contained, but they're not necessarily equal, right? We can have, these parity checks can have very small rank, right? So the span of the rows here can be small compared to the size of this code. So when these two R's are small compared to n, the code has some dimension. And how do we look at a word in the code? It's any word in CZ, but two words that are only different in a parity check are considered the same word because when you think of the words here, it's like an operator, like a code word can be thought of as a linear operator that moves you from one element in the code to another element in the code, right? If I have a code word and I add another code word, I get to another element in the code. So each code word is like a noise operator that confuses me. It moves me from the correct code word to some other code word in a way that the parity checks won't be able to tell. So every time I add a code word, it's like I'm doing some noise that is impossible to tell. And I'm interested in correcting noise that only makes a few errors. So one way to do that is to make sure that all my code words are very heavy. They flip a lot of bits. So similarly here, every element here is an operator that moves you from one correct state in the code to another correct state in the code. Now, CZ contains CX perp, so these guys are also operators that move me from one state to another, but because they're parity checks, they actually leave me in the same state. So these are not considered errors. That's why really the set of different code words that are interesting to study is this quotient, CZ divided by CX perp. Now, take it with a grain of salt. If you're interested in this, you should study it. There are a lot of material is available, both online and a lot of text. So I'm just kind of saying a few.
So if two different words from CZ are both orthogonal, choose the same word in CX, we consider them the same.
No, what is this space? It's the set of cosets. So if two words here, their sum is an element here, they're the same. Okay, so this is the set of code words, and it's symmetric. I can also view it as CX divided by CZ perp. And now we want to understand what is the distance of the code, or how many errors can you correct. You want to understand what is a word here that is in CZ but not in CX perp and has smallest weight. So this is what you care about. So the distance. Okay, so let me erase this and say, okay, code words correspond to this, to C. To CZ divided by CX perp. or to Cx divided by Cz perp, okay? The dimension we said, and the distance is the minimum between the x distance and the z distance, where the x distance is the minimum weight of W in Cx minus Cz perp. So we look at all the elements in Cx, but we don't allow elements here. And similarly, dz is the minimum weight of elements in Cz that are not in Cx perp. Okay. And finally, we say that a code is LDPC if all parity checks are, low density, meaning a constant number of ones. Okay, so if these both of these matrices have a few ones in every row, then the code is LDPC. And it turns out that this chain that we drew over here, okay, I didn't say how this corresponds to a chain complex. So this is a definition of a quantum CSS code. It's given by two parity check matrices whose rows are orthogonal, and this is how you define the dimension and the distance. Okay, now it turns out that this is equivalent to having a two chain. Okay, so basically you start from some space, you move by HZ transposed, you move to this is where the qubit, this is where the code lies, and then you move by HX to V2. So whenever you have two matrices that are, the rows are orthogonal, you can define this linear map. Let's see. HZ transposed is something that is n by RZ. HX is something that is Rx by n. So here I take RZ bits and I move to n bits by HZ transposed, and then I move to Rx bits, right, when I move by HX. Okay, so I start with a word that's RZ long, I do this matrix multiplication, I get an n-bit long vector, and then I take this n-bit long vector and I multiply it by this guy and I get an Rx long bit vector. And to convince myself that this is a chain complex, I need to show that the image of HZ transposed is contained in the kernel of HX. And this is exactly, what does it mean? What is the image of HZ transposed? HZ transposed is all linear combinations of these columns. Okay, but now this was the transposed of HZ, so all of these guys are just the rows of HZ. Okay, and I know that every row of HZ is perpendicular to every row of HX, so it's exactly contained in all of these, in this kernel. Okay, so it means that this is indeed, so this is a chain complex. And you see that what is the cohomology here? The kernel divided by the image, this divided by this, is exactly Cx divided by Cz perp. So this is the code words. So the code words correspond to the cohomology. Ker Hx divided by im HZ transposed. Okay, and so you can now try to see if you have a good chain complex, maybe it gives you a good quantum code. And the interesting thing, so if you choose the parameters for CA and CB appropriately, we actually want one of the CAs to have high dimension, like 1 minus epsilon, and the other to have epsilon, and then you will get that your code has dimension. So I'm not going to do the calculation, but I do want to say a couple of words about distance. Okay, because it turns that the proof of distance is very similar to the proof that we did here for local testability. Okay. So let me try to prove distance. I'm looking at this picture over here, and this is my 2 chain that I'm going to use for a quantum LDPC. Actually, let me erase and see. So it turns out that gives a quantum LDPC as long as, so previously we said that something like CA tensor CB was a coboundary expander. Now we need to prove distance both for dx and for dz, which turns out that you need to look at this chain with the arrows also in reverse. You need to take the transposed of all the arrows and look at this chain this way. And I'm not going to do it, but it means that you need to look at the dual code, CA dual tensor CB dual, and it also needs to be a coboundary expander. Okay, so as long as these 2 things happen, you have constant relative rate, constant relative distance for this chain. And let's just do the distance. So distance in this direction. Okay, so what I need to figure out is if I have some chain in the middle, for every edge I have a code word in this chain. I want to show that either it's actually completely in the image of something coming from below, so it's in the image of delta 0, or if it's not in the image of delta 0, it must be high weight. Okay, so I want to show that for every f in, how did we call it? I guess z2k to the x1, if f is not in the image of delta 0, then the weight of f is large. Okay, so by the weight of f, I'm just thinking the number of edges for which what's written on the edge is non-zero. Okay, so this is a set of edges, and really what I need to prove here is that, so let me define, let E prime, just suggestive name, be the support of this f. Okay, and I want to prove this E prime is large. Okay, this is what I need to prove when I want to prove distance. And the first step that I will do is make sure that f is locally minimal with respect to vertex moves. So I'm starting with a function that's outside this vector space. I'm going to now make moves by adding to this function elements in this vector space. No matter how many elements I will add, I will never reach 0. Okay, I forgot to, I will never reach 0, right? Because I'm outside this vector space. Okay, so I'm going to make these vertex moves. Basically, I'm going to always add to f. I'm going to choose a vertex G, choose some matrix k by k, encode it, and then see what it does on the edges. And if it causes more edges to be 0 than before, I will do it. Do you understand what I'm doing? I'm starting with the function f. This function, if I think of it pictorially, like this is my entire complex. I have vertices and edges, and this function gives me, on every edge, there's a little k-bit string. Here there's a k-bit string. There's a k-bit string. So this is my f. On every edge there's a k-bit string, and suppose f is a function that doesn't come from starting out with a k-squared bit string on every vertex and mapping it out. Now I want to show that f must have high weight. So I'm saying, okay, suppose I'm given this f, and maybe there's a value here, every vertex I can put some k-squared bits here, so that when I map them, when I stretch them this way and put them on these edges and stretch them that way and put them on those edges, maybe I can cause more of these edges to be 0. If so, this is called a good vertex move. So I make this move. And I repeat and repeat and repeat until I'm stuck and I can no longer reduce the weight of f. In this case, I call f minimal. So without loss of generality, I'm going to prove that after I did this, the weight of f is large. This will, of course, imply that even before I did all these moves, the weight of f was large. Okay, so we assume, without loss of generality, that f is minimal with respect to vertex moves. Okay. And now I'm going to look at the set of edges where f is non-zero, and I'm going to actually just try to repeat the argument that we did before, but now I'm going to use the fact that these guys are code words. Okay, so I think I'm probably a bit too tired to do the argument, but the argument, I wrote it in the notes. The argument kind of follows exactly the same steps as the argument we did over here. Yeah, I guess I said something wrong. I should say that f is not only just a chain, it's really supposed to be more than just being a chain, it's in the kernel of delta 1. Right? So it's a code word, so it's in the kernel of delta 1, but it's not in the image of delta 0. So it's in the kernel of delta 1, but not the image of delta 0. And because f is in the kernel of delta 1, it must satisfy certain consistency constraints that will mean that if this edge is non-zero, then on every square, some other edges around this square must be non-zero, and the exact same reasoning as we did before will follow. So, okay, let me not do it because it's better to look at it in the notes if you want, and let me try to back up and summarize what's going on here. Okay, so actually two different threads of work came up with this left-right complex, and one of them showed that this is an LTC and a quantum LDPC, and I only showed part of it. And what's interesting here is that you see that the 2-chain in the quantum LDPC code, it's inherent in the way the code is defined. And the distance of the code turns out to be equivalent to a statement about if a function is locally minimal, then it has to be large. Whereas for proving classical local stability, again you have the same kind of statement, that if a function, where is it? Okay, we had it somewhere. If it was locally minimal, I guess it's not here anymore, then the set E prime had to be large. And this is also very similar to how we proved cosystolic expansion. We started with some set of edges, we made some local vertex moves, and then we said, you know what, after we finish making these moves, either what we have is small or, is 0 or it must be large. So you have the same propagation argument underlying all of these things. So I think it's interesting and kind of, I don't think I fully understand it, but I thought it would be nice to describe it. It's kind of very recent developments here. Okay, so next week I will continue to talk about agreement testing, but no longer in this homological terms and no longer in this QLDPC world, but more in things related to PCPs. So that will be next week.